Good evening, everyone. I'm Akshay Jain, and I am also a 5G or a ESR PhD student here. And yeah, I came here in September. Before this, I was in the United States. I did my master's from University of Florida in Signals and Systems, and then I was a co-founder at a startup, drone startup. So we used to make swarm systems. And so I was the lead communication systems engineer there, and from there I'm here to do my PhD for mobility management mechanisms in current and 5G wireless networks. That is what my presentation is going to be on. So what is the agenda? We need to know the agenda, we need to know the flow, and so this is it. So I'm going to start from the very basic, what is mobility management? We're going to talk about mobility management in general. We're going to talk about what it really means, because it's essential to what we really need to understand what's going to happen in the future networks. So what are the current methods? What is going on right now? And what are the current and future scenarios? Okay, so it's going to be really different, and we need to know what is going to be different. So we need to look at the present and at the future so that we can determine what are the issues faced by the current methods. Once we know the issues, we need to know what are the expectations and what are the determining factors that we have from the future mobility management mechanisms. And then, is there anything right now that can help us in the future? Let's see. And then you look at the current research efforts. There is an extensive effort by the European Union and South Korea and a bit from the United States to really come up with mechanisms to deal with 5G networks. And projects such as the METIS or iJoin or 5G Aura, 5G Norma, these are projects which are really driving the research forward, and so there are a lot of research efforts currently out there which try and tackle the issue but not completely. And then we look at the challenges which are still persistent and which will be there. So, what is mobility management? So consider you have an access router and you have access points and your user equipment is actually connected to this one, but it starts to move. So for example, you get on a train from Castelldefels, you start going to Barcelona, and you start to leave one base station, you start to connect to the other base station. So the green link shows that you're getting better RSSI or SNR or SINR, whatever your parameter is to connect to. And so what happens is you hand over, and so the mobility management mechanism right now, what it's trying to do is it's trying to select a good radio access, a good rack or a good access point, and it's trying to reconfigure the flow through the access point you're trying to connect to, because it has to now redirect all the flows that you had at the previous access point to the new access point. Its responsibility is to reduce the service outage time and to ensure that you have the required quality of service whilst you're in mobility. So that is what mobility management does right now in general. Okay, there can be specifics, but I'm not here to deal with the specifics of current technology. We are trying to explore what mobility management will be like in 5G networks. So what are the current methods that help you to, in general, deal with the things that I was talking about in the previous slide? And so, so this is the figure that we were talking about. And so you look at it, at the layer 2, it's trying to attach you to a new access point. So you have an RSSI based mechanism in general, because it encompasses SNR and SINR as well. So you're looking at RSSI and you say, okay, this base station is better than the previous one, I'll attach to it. That's layer 2. At layer 3, if you change your point of attachment, you go to a new router, and if you have existing flows, then you have mechanisms like the mobile IPv6 or the proxy mobile IPv6. Now, this thing is very significant, the proxy mobile IPv6, because LTE sort of adapts to that sort of a mechanism. So it's a network centric, so you don't need software upgrades on your user equipment in general. So these mechanisms, as proposed by IETF, what they allow you to do is they allow you to redirect flows if you're changing your access router, or they allow you to be mobile within the network if you change your domain. And so they also provide data forwarding, as I just talked about, as well as route optimization. So in case your forwarding chain becomes too long, and if you have a shorter route to your node which you are communicating with, it will optimize the route and it will reduce the amount of time you take to traverse through the core network. So with that in mind, we look at what are the current scenarios. What is the network like today? And these methods that I was talking about, they really serve the current scenario very well, but that's not going to be the case. So this is the current scenario. It's a very crude diagram to show the current scenario. It's not the full picture, but we need to get the idea and not the details here. So if you look at it, you have a Node B BTS which represents 2G and 3G technology. You have LTE Node B which represents the current 4th generation, and then you have user equipments which might be smartphones, legacy users, things like that. So it's a very generic network, it's very understandable what goes on right now, but this is the future scenario. It's very dense. You've got small cells. Those small cells, it's dense, it's heterogeneous because you've got Node B BTS, LTE Node B, and then you also have small cells which might be LTE based or Wi-Fi based. And you will also have the 5G physical layer which will also come into the picture. So it's highly heterogeneous. It is highly dense, not just in terms of the number of users, but also in terms of the number of access points that are going to be there. And it's got smartphones, legacy users, Wi-Fi only devices, as well as sensors. So sensors, for example, I think narrowband LTE was recently standardized, and so we are moving towards a generation of technologies where you just don't have these broadband services and call and voice services. You also have sensors which are being served by the core network. So with this huge change, there are a lot of issues that pop up. One is the ping pong effect. It's already there, it's going to be magnified. Okay, with RSSI, for example, you have a base station here, you have a base station right here, and I'm here. It's going to keep ping-ponging back from one base station to the other. When the distance was this large, you still had those effects. So you're going to increase those effects. Frequent handovers. If I move through just 10 meters, 20 meters, I'm going to be experiencing so many base stations trying to tell me, hey, I'm better than this guy, I'm better than this guy, I'm better than this guy. You're going to have so many handovers if you try to go with just an RSSI-based approach. There's going to be congestion. For example, if I'm using the current method, what will happen is that the network will try and attach one user to an access point that has better signal quality. Now, for example, if there's just one access point which is telling me this, then it will try and attach everybody to that access point, and you're congesting it, you're overloading that access point. Okay? So that's going to create issues. And if you're trying to attach to just one access point to all the users to one access point, then you're going to have degraded quality of service at that point because it does not have enough resources to deal with. High mobility support. Now, one of the stated objectives of 5G is to support mobility in the range of like up to 500 kilometers an hour in high-speed trains. So that isn't there right now. And that is one of the issues. It's not a burning issue, but these are all like major issues, but you still need to provide that. And then network slicing support, as I talked about, sensors are going to be there, there is going to be connected cars, there's going to be critical services, there's going to be broadband services. So you need to be able to support all of these services with different requirements in a single core network. So the mobility management mechanisms have to adapt to the type of services being accessed. So, with these issues, we look at what are the expectations. And the expectations are, as my colleague already mentioned, to satisfy a less than 1 millisecond latency goal. But that is for critical services. But again, if you look at it, you have to make a handover decision. You have to execute that mechanism, and you have to attain it within this latency goal, to achieve this latency goal, and to allow for other network operations is a challenging expectation. Multi-slicing support, so there can be strategies where you can club multiple slices together. If they have, like for example, if the users aren't moving and you have static sensors, you can probably club their mobility patterns together and you can create a common strategy. Or you can have individual strategies for different sets of services. So things like those, seamless connectivity amongst multiple racks, because you have so many different radio access technologies like Wi-Fi, LTE, 3G, 2G, and the 5G physical layer which will come in. And as my friend talked about, there's going to be a centralized RAN approach, or all of these will converge to a single core network. So to be able to support seamless connectivity amongst multiple racks is another issue. Computational tractability of algorithms. By this I mean that, again, you have so many different levels at which you can deal with mobility. Like you can deal with it at the cloud RAN level where you have the access points. So if you're just switching access points, you can decide on which one you have to go to. At the network level, you need to restructure the flow so that it supports the mobility. So when these algorithms run together, you have to look at how much computational complexity you are incurring, because you want to be you want to be really proactive, you want to be fast when dealing with mobility in these scenarios, because it's highly dense. And so to ensure the best quality of service, you have to be at it all the time, like, what is the best access point I can connect to. And so that is very important. And then support for legacy devices. Okay, we cannot throw away the legacy devices here. We need to still support them, even if we move towards centralized architecture, a softwareized architecture, you need to be still able to support them. So those are the expectations. The defining factors, these are the core principles that need to be kept in mind when we design the new mobility management schemes. And so these are, flexibility is very important, because if your mobility management scheme is rigid like the RSSI based approach, it cannot be a one-size-fits-all approach, because your sensors might, they incur zero mobility, you might not need any mobility management support for them, whilst people accessing delay sensitive services like you're playing a video, you need extensive mobility support in those scenarios. So it cannot be a one-size-fits-all approach. Granularity and flexibility, they are very closely connected, because when I talk about granularity, it means that, okay, I might be accessing a service that needs mobility support like a video, and I might also be accessing a service which does not need mobility support. So there are two different flows on a single user equipment. So to be able to differentiate the flows on a single user equipment, or to be able to differentiate the mobility profiles of different users, I am mobile, you're not. So I don't need to have a mobility management, profile for you, but for me you might need a mobility management profile, because I am moving and I have some services which need that support. So that is very important to keep in mind. Actually, we just have a paper on this, on the mobility management as a service, that talks about granularity. I've not listed it here, but if you go and search, it's on archive. So you can read about that, and it's really important. These are very closely linked together. Scalability, it's really, really important, because considering the density of the network, you will have more control plane traffic, you will have more data plane traffic, and you need to be able to scale your network as the number of users grow. And for example, if I consider PMIP P6, it's a centralized approach. It has a centralized node which controls the network prefixes, and then you have it's called the LMA, the term, and then you have the MAX, which are dealing with the mobile node. But all of the handling is done at the LMA, and it creates a problem if you have a highly dense network. So the scalability is also at the forefront of creating an effective mobility management scheme. So I've talked about all of this. I've bashed the current network. I've bashed I've created enough negativity in all of our minds that current networks are not good, current methods are not good, but it cannot be that people did not see this coming. And so there are some methods which can really help us through. And so they are, the ITU proposed a vertical multi-homing approach. Now, multi-homing means you can have multiple connections. And by vertical multi-homing, they're trying to say, well, you can have different racks, and you can have different paths through those racks. So you can ensure reliability of service through that. Then IEEE proposed 802.21. So it's a messaging, it's an information service basically, but it allows you to gather that information from different radio access technologies like .16, .11, .15, and to allow you to perform an interact handover between those technologies. IETF has actually a distributed mobility management working group. So they have two RFCs which are informational. They are not standards level yet, but they have come out with certain ideas as to what people should do when trying to design a distributed mobility management approach. By distributed mobility management, you can primarily distribute your data plane, as in you don't need to, there is no home agent here that you need to source all of it flows through that. But you can also distribute your control plane. So it can be either fully distributed, wherein your control and data plane are totally distributed. You don't need a central controller to handle your routers. Or it can be partially distributed, wherein you have a controller which takes care of the control messages, but the data plane is still separated out. And then you have a SDN-based approach, wherein you have an SDN controller that's controlling your access router. So it can send open flow messages, and it can configure the paths, and you can have packet forwarding on that basis. And if you're talking about P for programmability, you might as well talk about more flexibility in the network in that way. I'm sorry, I forgot a dash here because it's not uniform. So LTE-X2, it's an X2 handover. We generally don't, we talk about LTE being a flat architecture, and this is one of the reasons, because it has an X2 interface, and what it allows us to do is it does not necessarily need to go through the core network if you're performing some mobility management and if you want to do data forwarding. You don't need to go through the core network. You can go, if you have an X2 interface between two eNode bees, they can actually talk, they can do resource negotiation, and they can actually start packet forwarding. So you have fast handover, you're not going through the core network, so you're actually having a decentralized mobility management at that point. So, these things can play a role in what we plan for the future. So, with this, let's recognize the current efforts. RAT selection algorithms. I'm not going to go in deep details. It can be very extensive, it can be very exhaustive. So what I'm going to do is I'm going to summarize them, and I'm going to talk about certain pros and cons, not for everything, but for some things. So RAT selection algorithms, this is like at the lower level, you have your access point, you're moving within one domain, and you switch an access point. So how do you select the appropriate radio access technology? And so what are the algorithmic approaches they're thinking about? One is the optimization approach. Now, when you do optimization, you have a certain set of parameters you can look at, okay? So I might look at the network load, I might look at congestion, I might look at the user density in the particular network, and you can formulate optimization strategies based on that on your, say, a Cloud RAN, which is handling your remote radio heads, okay? So since Cloud RAN is also softwareized, you have the full flexibility to have a global view of your domain, and you can do an optimization-based approach. The problem with this strategy is your problem convex? And the convexity of the problem is what will be a defining factor, because then what comes into play is the computational complexity, and you want it to be fast. So there is going to be a trade-off between which parameters you take into consideration, which ones do you not, and how do you formulate your problem. So those are some of the issues. Fuzzy logic-based approaches, they tend to achieve the optimal solution, but again, they take a lot of time to really do the computation. And honestly, in my opinion, these approaches, due to their time complexity, are not very attractive. People have proposed papers, there's a lot of research in that, but time complexity is something that people are still trying to figure out with these strategies. This one, SNR or SSI based approaches we have discussed. These are current strategies. Very simple, they're scalable because it's easy to perform for almost every node that comes into consideration. But again, the issue is it's going to be a dense approach, it's going to be a dense network, and so they will face problems, as we have already discussed. Traffic offloading. Traffic offloading is basically a network engineering sort of strategy, wherein you try to offload some traffic onto another radio access technology, or if you're doing some traffic transfer to reduce the load in the network. But implicitly, this implies that some of the users who are being reallocated to a new access point or to a new radio access technology will have to undergo a handover. And that is what people are also looking at, like how to select the radio access technology to which we move to. And that also comes under mobility management. SDN-based approaches. Now, software-defined networking is very popular. People have talked about it. how do you do SDN? SDN will allow you to separate the control plane, the data plane, and it gives you all sorts of flexibility. Well, there are different ways to do things. For example, if you have a totally centralized controller, yes, you have the full global view, you can have the most optimal solution. Problem, it is centralized. There is a single point of failure, and it is an issue. And also, if you have too many users being connected, how many open flow rules can you push to the routers? And what is the control plane latency that you're going to achieve? Because you need reactivity, you need the appropriate control plane bandwidth, and you need to keep the control plane latency in check. So that is very important. Semi-centralized approach, okay, you have distributed, you have multiple domains, SDN domains, and these SDN controllers, so you have SDN controllers that talk to each other, and they control their separate domains, and they can talk to each other. But again, there will be latency when you move from one SDN domain to the other because you need to exchange information between the SDN controllers. And then you have the hierarchical approach where you have a global SDN controller and you have these SDN domains. So the global controller has a global view and it can have slow optimizations on your local domains, keeping in mind what the global view is, and then your local SDN controllers can control their own domains. So those sort of strategies. And the distributed mobility management approaches, I've already explained this. And so fully distributed, you have total distribution and control and data plane. Partially distributed, you have a centralized controller, but a distributed data plane and SDN-based DML. The SDN takes care of all the control plane. Not all is rosy, we still have challenges. Time complexity of algorithms is important. You need to ensure the system latency. We need to ensure that we support multiple network slices. Scalability, flexibility, and granularity are the core principles, they are the pillars. We need to account for user and network requirements and policies. That is very important. You cannot have an independent reaction here. You need to take care of policies and requirements from both the entities. And we need to take care of the ping pong effects and frequent handovers because it's not an easy problem to deal with. Any questions?
So, any questions from the audience? No?
It's like a good presentation. Yeah.
Can you explain the granularity a bit more and confused about this?
Yeah, so let me go back.
Maybe in the third slide.
Yeah, this one, right?
Yeah.
So, when you talk about granularity, for example, right now, if I have a video service that's running and if I have another application that does not require data forwarding or, real-time approach, okay? For example, real-time approach. What happens is I still get the same mobility context. I'm still offered the same services, even if I have a flow that requires mobility management or if I don't require mobility management. Now, that is inefficient, okay? And if you expand that out to other users, for example, you have your cell phone, you're still assigned a mobility context, and I'm also assigned a mobility context, but I'm moving at 30 kilometers an hour, I need it, but you're stationary, you don't need it. Assigning mobility context to users who don't need it is inefficient. Assigning mobility context to flows who don't need it is inefficient. So you're trying to look deeper. You're trying to introduce the granularity in the sense that you're trying to look at each flow on its merit. You're trying to look at each user on its merit. You're trying to look at each user's mobility profile on its merit that doesn't need a mobility context. If I'm sitting at home, I don't need mobility. Okay. I can just sit there at home and I can use my services even if it's delay sensitive or delay tolerant without a mobility context. Because
suddenly I might have something to go out.
But it's all statistical in nature, so they will. So they're not pinpointing you as a user. They're allocating resources based on, like, for example, they say, oh, I serve 100 users every day, and of this, I think statistically 80 users need mobility context. So, you only have those many resources and you start assigning based on that, okay? And if you have 80 slots available and if you service 75 people, it's good. There might be situations where you need 85 slots, but you get the gist of it, that you don't want to unnecessarily allocate resources to people, okay? So, it's based on on merit, on demand resource allocation is at the heart of granularity concept. So, yeah.
I have another question.
Yeah.
Among the different factors that could drive the mobility management, for example, I can think of the state of the backhaul, for example.
Yeah,
and
I'm sorry I did not include it here, but it is, I think it's in the paper, but it's not here. I'm sorry about that, it should be here. Yeah, because the state of backhaul is really important because, you know, if you're talking about resources in the backhaul, then it's going to be heterogeneous. If I'm assigned to an access point where I don't have really any backhaul resources available, it's of no use because my quality of service is going to go down anyways. So, you know, that is another, like when you talk about optimization approaches, that has to be considered here. Okay, that has to be a factor in this. It is a very important factor and we cannot deny that. So yeah, you're right. I mean, the backhaul resources have to be considered, have to be factored in.
Yeah, my point was, are you thinking in doing something together in?
Yes. We
already have an idea.
Yeah, we have an idea. The paper that we wrote for CSCN,
yes,
I think, yeah, that is something that we want to work on. So, you know, when we start to converge, the idea is to converge on our ideas.
Either of us will be putting that paper in our research proposal.
Yeah, we'll see how we can work that out. But yeah, the goal is to have the both of us converging to that at the end of it, because I think that is something that is very sparsely looked at in terms of the research community. I have read a paper where they talk about the LTE backhaul for mobility management, but they go as far as just characterizing the number of hops, but not consider, because it's LTE backhaul, it's not heterogeneous.
Yeah, that's quite novel. I mean, this approach could be quite novel.
Yeah. So that's kind of the idea to do it, to converge.
Okay, thank you.
Yeah, thank you.
When we talk about internet protocol, inherently the mobility is not supported when it was designed. So do you think that these technologies we are working on will support or can get rid of that issue of IP protocol?
So inherently they were not there, but as you look at where is that? Okay, yeah. If you look at this, the IETF already had like mobile IP before, you know, those techniques to actually handle mobility in networks. So things are there to handle mobility. The issue right now is the network is scaling up so fast and it's becoming dense. You have a cellular network now. I don't think you'll be able to define your future network as a cellular network because it's going to be just so, I think it's a wrong term to say, but it's going to be just so frenetic in like where your access points are, where your users are, so dense and everything together that you cannot use those ideas anymore. Okay, you need new mechanisms to deal with it, but you know, the idea was, can we use some of the past technology ideas to really help us out in the future? Okay, so you already have mechanisms to deal with mobility right now. That is how we are dealing with, but then we cannot use them here and in whole, but in part we can actually utilize their concepts to, you know, develop our future mechanisms. So that's the idea, really. So yeah, I mean, I think we can use a part of them, but not completely. We need to modify certain things. We need to look at the whole network architecture, and you know, what are the different things we can really look at. What are the different scenarios that we can look at? It's a very what I say. It is not impossible, but it is a very, you know, vast problem. So you need to deal with it from different angles for different scenarios. So yeah.
Okay, so
correct. Thank you so
very much
yeah.
for these two very inspiring talks.
Thank you. Thank you. Or if you have any queries, you can go there, or you can check my website.